All right, so we're going to run through this example real quick. So this is the xylitol and ear infection example. So if we remember, we have the first sample has 165 children, 68 of which got an ear infection. This is the placebo. And in the second sample, we had 159 children, 46 of them got ear infections, and that's the xylitol sample. So our H naught right here is P1 minus P2 is 0. And if we think, right, if we go right here, we believe the proportion of ear infections in the placebo group will be greater than the xylitol group. So we believe that the proportion in the first group is going to be greater than the second group. So we believe that P1 is greater than P2, which allows us to pull them both to the same side and have P1 minus P2 is greater than 0. And this is our claim. And this gives us a right-tailed test. So we're going to find the critical value. So we're going to find the z associated with 1 minus 0.025 because it's right tail. So we want 1 minus our alpha. And that gives us 0.975. And when we look that up in our z table, we get 1.96. Remember, there's multiple ways to do this. If you wanted to leave alpha as is, you would get a negative critical value, right? You would get negative 1.96. And because you know that you're doing a right tail test, you would just make that positive. So if you don't want to do this extra step of 1 minus, that's perfectly fine. That's how we've been doing it. But again, I think at this point, we've done enough that I hope that we understand what we're actually looking for and that there's multiple ways to actually get where we want to go. All right, so now we're going to compute the test value and then determine the p-value. So using this equation right here, p hat 1 minus p hat 2 minus P1 minus P2, which is 0 by our null hypothesis, divided by P bar, square root of P bar Q bar, 1 over times 1 over the number of sample size of the first sample and plus 1 over the sample size of the second. So let's do some calculating. We're going to go over here to the right. We have P1 is the number of successes, or the the number of yeses, or the number of whatever you want. In this case, we're talking about the number of ear infections. So 68 over the total number 165, 0.41. P hat 2, 46 over 159 is 0.29. P bar, we're going to take all of the successes or all of the notable events, so 68 plus 46, and divide it by all of the participants in both samples. So 165 plus 159, we get 0.35. Q bar is just 1 minus 0.35 is 0.65. Plug all that into your calculator and we get a z-test of 2.263. If we want to calculate a p-value of that, we can go right over here to Excel, and you'll see that I have 1 minus norm dot s dist, and I plug in my z value right here, this 2.236, and then it'll ask for a cumulative, right? And that's just 1, right? We're interested in the whole thing. Now that gave me a large, right? Because that's going to give me everything to the left. So that was 0.9 something or another, and then I just did 1 minus that to get, right, we want this little chunk out here. If we have 2.236, we're just interested in this chunk right here, this area or this probability. And so when we look up 2.26 in our table, or if we use Excel, remember it's going to give us everything this direction, so we need to do 1 minus that. Now, given that our alpha is 0.025 and our p-value is 0.0127, our p-value is less than our alpha, and so we get to reject the null hypothesis. And we would summarize the results to say there's enough evidence to reject the null hypothesis and support H1, or you could write that out, and support the claim that the placebo group has a higher proportion of ear infections than the non-placebo group. So that's written out fully. Okay, let's do another example. So in an example of 200 surgeons, 15% thought that the government should control healthcare. In a sample of 200 general practitioners, 21% felt the same way. At alpha equals 0.01, is there a difference in the proportions? So we have 2 different healthcare professionals. We have surgeons and general practitioners, and we're trying to figure out if we can say that there's statistical evidence that they have a difference in beliefs about this particular issue, right? In the way government should control healthcare. So our H naught, right, P1 minus P2 is 0. Our H1, since we're interested in just is there a difference in proportions, it's P1 minus P2 is just not equal to 0. So this is our claim, and this makes it a two-tailed test. So first step, we're going to find, or second step, we're going to find the critical value. So we're going to do Z associated with 1 minus alpha over 2, or 0.995. And if you look this up, you get 2.58, right? If you look up 0.995, you get 2.58. And since we know that it's two-tail, there's also a negative 2.58. Similarly, you could just leave it as 0.01 and look that up, and you would get you would get negative 2.58, which now that's the left side, and so we want the right side, and so we can just make that 2.58. Okay, so now let's compute the test value and determine the p-value. So I am going to start right here. So we have p hat 1 is 0.15. They tell us that. P hat 2 is 0.21. The problem is that we need x1 and x2 for p hat, right? P hat is x1 plus x2 over n1 plus n2. But that's okay, because we know that p hat is equal to x over n, right? So p hat 1, which is 0.15, is equal to x1 over n1. And we have n1, don't we? So we can just multiply both sides by n1, and you get that x1 is equal to p hat 1 n1, which is 0.15 times 200, which is 30. Doing something similar with p2, and you get that x2 is p hat 2 times n2 equals 0.21 times 200 equals 42. So now we have all the ingredients we need. We can calculate our p bar right here. 30 plus 42 over 400 is 0.18. Our q bar right here is 1 minus p hat. P bar, excuse me, is 0.82. So you come over here. So we are at this area. So we're now going to do a z-test of p1 hat minus p2 hat minus, and this is going to be a 0, remember by assumption, p1 minus p2 is 0, divided by all this good stuff over here. And if you do that, you get a z-test equals negative 1.56. So if you look that up in the table, you're going to get a p-value of 0.059, but we have to be careful because that, remember, is just going to be the stuff to the left, but we now are interested, because two-tail, we are interested in what could be to the right. And because of symmetry, we know that there's also a 0.059 area or probability hanging out to the right. So we're just going to double it to get a final p-value of 0.119. All right, so let's make a decision to reject or not reject the null hypothesis. So we could do this as a z-test. So we've got our rejection region over here to the left of negative 2.58 and to the right of 2.58, and negative 1.56 falls in our non-rejection region. So we don't reject. Comparing p-values, our alpha is 0.01 and our p-value is 0.119. Therefore, our p-value is greater than alpha. We don't reject, right? Again, we expect that whatever we do for one, we're going to do for the other. Therefore, there's not enough evidence to reject the null hypothesis and support the claim that ... right? So this one, the only difference with this one was that we didn't have an x1 and an x2, right? In the earlier example, we didn't have a p1 and p1 hat and p hat 2, so we had to calculate them, right? We had to calculate them right here. But in this example, we actually have the opposite, where we don't have the x's, so we can't, so we can't calculate p bar, so we have to solve for the x's, which we do right here, and then where we do right here, and then right here. Okay, So again, that's just about the same kind of thing. They just threw us a curveball by not giving us the x's. So let's come down here and do an Excel example. So in a random sample of 200 men, 130 said they use seatbelts. In a random sample of 300 women, 163 said they use seatbelts. Test the claim that men are more safety conscious than women. So we're going to say the claim is that the proportion of men that use seatbelts is greater than the proportion of women that use seatbelts, or, right, this tells us that our H naught, our H naught, P1 minus P2 is 0. H1, the proportion of men is that where seatbelts is greater than the proportion of women, which we transform into P1 minus P2 greater than 0. We get another nice right tail test. Okay, so let's swing on over to Excel. So we have our X, 300 and 163. Yep. And we have our N, so 200 and then 300. So to calculate P hat, you can see here I have just equals 130 divided by 200. I could also just do this as equals, and I'm going to choose X divided by 200. We get the same thing. And over here, I have 163 divided by 300. Again, we could just do equals this one divided by that one. Fantastic. So P bar, right? I added, right? If we click here, we can see everything. I have B4, so that's 130 plus 163 divided by B5, 200 plus 300. Now, what's really important when you do this is to get your parentheses right. You want it to add these two numbers first, and then add these two numbers second, right on bottom, and then divide them, right? Remember PEMDAS. So it's going to do what's in parentheses first. So we're telling it add B4 and D4, set that to the side. Add B5 and D5, set that to the side. Now divide them, right? So we want to make sure that our parentheses that our parentheses are correct. Now that we have this, we need to calculate our test statistic. So I did the standardized method where I did, the first thing that we want is our X value, the value that we're trying to standardize. And since we're trying to standardize the difference in proportions, the value that we're going to put in here is P hat 1 minus P hat 2. The second value is the difference in proportions, right? The P1 minus P2, which by assumption is 0. And then the third value is this standard error, which we calculate. This is definitely a bit tough, but this is our P bar, right? This B8. Excuse me, I skipped a step. Let's jump over here to P bar. So now that we have our P bar right here, we're going to calculate the standard error. And the standard error is P bar, so this B8 times 1 minus P bar, which is our Q bar. So we did 1 minus, and then we have B8 shows up again. And then times 1 divided by B5, so 1 divided by 200 plus 1 divided by 300. And all of that is under the square root. And that gives us a nice standard error of 0.045. So now we're going to swing it over to our test statistic. And our test statistic, I've chosen to use the standardized function. Again, you could just put this in, you could just write it out in terms of, equals ... The standardized function, you have to give it the thing you want to standardize. And in our case, we're interested in standardizing the P1 hat minus P2 hat. So I did D7, so P1 hat minus P2 hat. The second thing that goes in the function is the difference in P1 and P2, which by assumption is 0. And the third thing is our standard error, or that big nasty square root, p bar, q bar, all that good stuff. When you do that, you get a nice 2.372. We're now going to go over here and calculate the p-value, which I did the 1 minus norm dot s dist, and we have 236, excuse me, the test statistic. So actually I can just erase this and click on that. There you go. So we have, I just put in a rounded one, but we're going to use the exact one. So 1 minus norm dot s dot dist, and then we're going to put in our test statistic, and then 1, right? The cumulative, remember, it's always just 1, right? Because we're interested in the whole thing. Now that's going to return a very large value, because that's going to return everything to the left, but it's a right tail, and we're interested in everything to the right. So we're going to do 1 minus the value it gives us, and we just get this 0.08839. Now, if we go back to our alpha is 0.01. So do we get to, oh, excuse me, that's my calendar. Do we get to reject the hypothesis? And the answer is yes, right? This p-value is actually less than 0.008. Assume, yeah, p-value of 0.008939 is less than our alpha. So we do in fact get to reject.